This is our ECD World headquarters in Milwaukee, Oregon. It looks about like this today. It's overcast, wet. This is Grant Peterson, our VP of Marketing. This is me down here in the lower left. We have Paul Austin. He'll be your presenter today. Senior engineer, project manager, whatever. And Rex Brunsbach, our founder and chief. This is part of our ECDU family of classes that we offer. This happens to be profiling A to Z. It falls into this area of our ThQM, which Paul will go over shortly. If you're interested in any of the other classes we have to offer, please go to our website under training. We have a quarterly list of classes that we'll be giving. Of course, they're always free to attend. Today's outline, Paul's going to tell you about thermal quality management as it relates to electronics manufacturing. We're going to talk about solder paste requirements, about generating recipes for our ovens, what's needed to profile, how to determine the points to profile, attaching thermocouples, and actually performing the profile itself. With that being said, I'm going to go ahead and pass this off to Paul Austin.
Thanks. Thank you, Mark. Appreciate the introduction. I hope to put check boxes in all of those points. It is my understanding, and I think a good bet that you're here today because you recognize that profiling, at least thermal profiling of electronic products through your reflow process or your soldering processes is the way to reduce scrap and increase yields. It's also a very marketable service. It expresses a concern for your processes and their impact on the products you're soldering. That's kind of the heart of thermal quality management, which we've divided up into 3 different stages. This is just a quick overview of the thermal quality management class that we also offer. It breaks down into a requirement stage where we're literally defining the reasons for profiling. It's an understanding of heat-sensitive components, and it's an understanding of the solder technology and the requirements of it in order to make a good solder joint. Someone has to identify and determine whether components on your circuit board are at risk. So this is a very important step, whether your customer has provided that information to you or you yourself offer that as a service. Someone has to determine whether components are at risk. So this is probably the most important step in the thermal quality management program. However, there are 2 more. Somewhere along the line, we've got to decide what recipe it takes in the oven in order to produce or meet the needs of both the solder paste and the limits of the components. So you're developing machine settings required in order to meet the requirements. You assure that all solder joints experience the needed profile, and you assure that sensitive components have not experienced some sort of damage due to overheating. In many cases, that damage isn't visible. It happens later on by premature death of the product. And finally, verification. This is the stage that often is left off. It asks the question, how are we doing? It looks forward in time, as well as it allows you to look forward in time and say, I know my machine is going to perform well because I've been looking at it, I've been collecting data to show that it has performed well in the past. It's basically proof that your thermal processes are in control. So this is your data collection stage of the good thermal quality management program. And again, we do have a class on that. It's coming up here in the next few weeks, as I recall. out of ThQM, there's a couple of terms and definitions I definitely want to cover here. First, and these are two terms that get mixed up quite a bit when we work with contract manufacturers. That is profile. And basically, profile is very simply a graphical representation of temperature as a function of time. The profile is a recorded time versus temperature plot or graph. And that is not to be confused with, and by the way, this happens because you've measured the temperature of your product. This is not to be confused with the recipe, or basically the oven settings required to produce that profile. If you go to bake cookies, you set your recipe, you set your oven's recipe, or you set your oven for 350 degrees Fahrenheit, you put the cookies in, they cook them for so many minutes. That's the recipe. When you put them in the oven, they don't instantly snap up to 350 degrees. So just because your oven settings may be, your recipe may be relatively high in value, does not mean the actual temperature profile that the components or solder joints experience are anywhere near the value that the recipe may be set for. So we want to distinguish those. Quite often, a profile is used to describe a set of oven settings. I like to use the word recipe for the oven settings, and again, profile for the temperature that the parts experience. If you catch me switching those around, you can send us a nasty letter. So what can you control in the recipe? In most ovens, it's the zone set point temperature. It's the conveyor speed. And if you've got a nice oven, you can control the convection rate. And we'll talk about those a little bit more on how they impact the profile. Your oven may have other settings such as nitrogen on or off. There certainly are other parameters that may be settable within your oven, but these are the basic three. And in most cases, most people only have just the set points of the temperatures for the zones and the conveyor speed. So let's get into solder paste requirements. There are hundreds of pastes out there. And if you look at the brochure that comes with it, there are countless different alloys. There's countless combinations of alloys and different kinds of pastes, all of them in place to accomplish a certain thing with regard to solder joints. They all have one thing in common, and that is they all require a specific profile be met. And there are two basic profile shapes. The one we're going to focus on, which is the ramp soak spike profile, also known as RSS. It usually has an area that they call ramp, an area that they call soak, where you're basically holding at or trying to hold at a temperature which is usually just below the melting point of the solder. They have a spike region and then cooling, thus the name RSS or ramp soak spike. There is also the RTS, ramp to spike, which is characterized by pretty much a straight ramp up to the melting point of the temperature, a spike area where you take it over melting and then cool it down. Again, we are going to focus on the RSS, or what we call ramp soak spike type profiles. So what makes a good profile? Most solder paste manufacturers will agree that there are about 6 or 7 different parameters with regard to a solder profile that are most important. They are defined, or I should say extracted from the profile, centered around 3 different temperatures. First, the liquidus temperature, or what I've been calling the melting point of the solder. At the point in time, or I should say point in temperature, where the solder paste actually melts, or the solder alloy melts. There is also an end and a beginning temperature. These define the area around which we extract the slope value. The soak value. This end temperature may be at the liquidus temperature, or it may be slightly under. It varies a little bit, but there's always a beginning and an end temperature in a ramp soak spike profile. So what do we take from a profile? Well, first there's the ramp area, and this typically is a slope. It's in degrees, usually measured in degrees C. It's defined by from room temperature up to the beginning temperature, typically. So the ramp is always, if we use the term correctly, the area just from room temperature up to the beginning of the soak. Then there is the soak time, which is usually recorded in seconds. It's the time that the profile spends between the beginning and end temperature. Then we have a spike. Spike is typically is a slope, usually almost always measured in, again, degrees C per second, and it starts at the liquidus temperature up to the peak. There is a rate at which the temperature is increasing, and that's what defines what we call the spike. There is the time above liquidus, also known as TAL. Again, time in seconds. It is literally the amount of time spent above the liquidus temperature. It's important to note that half of that time, or usually about half, it may be a little less, but a good portion of that time is spent on the cool down part, which is usually in your cooling zone. So you're going to be heating to the peak, usually in the last heated zone or near the last heated zone, and then you're going to be spending the cool down or another portion of the time above liquidus in the cooling area of your oven as you go back down to the melting or the melting point or liquidus temperature. Finally, there's a peak temperature. That's very simple, the highest one seen. Not finally, there is one more. And finally, what we call our cooling slope, the rate at which you cool down. Typically, that's from the peak down to the liquidus. Once the solder paste is gone back to solid, you don't concern yourself too much. However, cooling has the same impact on your product as ramping and spiking. Fast ramp or spike rates can damage components. Fast cooling rates can do the same. I put an asterisk here around 4 of them. These are 4 parameters which most paste manufacturers agree are the most important 4. There are other parameters you could take from this profile. Obviously, these are usually the ones that most people or most solder pastes will emphasize, with the 4 here being the most important. Once we've identified the characteristic profile we're trying to achieve, we need to set oven recipe settings. And this requires some thought. I'm going to give you some general concepts on how this is done and then suggest a recipe for you. But there is software out there. We make it, our competitors make it. There's software out there that'll help you generate a recipe, and they're a good tool to start with. However, you cannot just say, hey, software, give me some numbers and call it good. You have to profile. You have to make sure that what you want is what you need. Software-generated recipes will base their recipe, the oven settings. They'll usually base it on one of 2 things: a similar board with profiling characteristics that you are currently or have used in the past or have profiled in the past, or it may be based on some knowledge of the oven's characteristics. Both of those require that some sort of profiling had been done on the oven in the past, either some standard board or some board that is similar to what you're about to solder. In either case, the software can help you generate recipes. You may do it on your own experience. Hey, I've soldered a board this approximately the same size, approximately the same component density, and therefore I'm going to start with this same recipe that I used on a similar board. And that's a perfectly good starting place. Either way, it's always best to undershoot the zone temperature settings for 2 reasons. One, it lowers the risk of destroying your board. If this board heats faster than the one that you maybe had used in the past, you don't want to destroy it because it may be the only one you have. And if you overdo it, It takes a whole lot longer for an oven to cool down than it does to heat up. And no matter how many times you open the lid and try to blow the heat out, it just seems to save it. So it's a whole lot easier to get the oven temperature up a bit if you start low and work your way up to the recipe that's ideal for your needs. So this is just some general thoughts on how recipes can be generated. Let's look back at what you control. We talked about there are 3 things you can control. Oven zone settings is the first one, or the temperatures for each zone. And these may seem obvious, but so often the obvious is ignored sometimes. Zone temperature basically gives you 2 controls, or it controls one basic thing, and that is heating rate, or what we call slope. Higher temperatures in a zone will cause your product to heat faster. And the larger the difference from where the product's temperature is right now and where that zone temperature is set, the faster it'll increase. So if you need to increase the rate at which a product is heating, you can increase the temperature. Of course, opposite is true. You lower the temperature, you're going to reduce the heating rate. Conveyor speed. This is also deceptive because you might be looking at a collection of zones in your oven or an area on the profile where you want to change something. Unfortunately, changing the conveyor speed changes the time spent in each zone, and it changes the time spent in all the zones. So slowing it down in the first 3 zones is going to slow it down in the last zone as well. Because we keep that in mind before you arbitrarily just say, I'm going to drop the conveyor speed. It affects the whole profile or all of the zones. Increasing and decreasing speed does nothing for slope. It just changes how long you spend in each zone. Thus, it changes how long that zone will have influence over the board while it is there. And let's face it, most zones are 12, 14 inches long, and you're only going to be there 20 or 30 seconds. Finally, convection rate, if that option is available to you, it's an excellent way to control how much heat is forced into the board, slope again, without changing the set point. Increased convection rates will cause boards to heat faster at the same set point. And the converse, well, maybe not converse, but an opposite is true, and that is you can lower the temperature set point and increase the convection rate and end up with the same heating rate. That's the beauty of convection, because it gets more heat into the board at lower settings, which means lower recipe settings reduce the chance of you cooking a board because you're dealing with temperature set points that are lower than, shall we say, the damaging temperatures. Higher convection rates help reduce the temperature differences between components in the profile. Components of completely different masses will heat more equally at higher convection rates. There are, of course, limits, and one of those is you don't want to blow the parts off the board. And there are ovens out there that, turned up high enough, will do just that. So here's some initial recipe settings that work quite well for a 9-zone oven. If you have fewer zones, you got to kind of compress some of these. If you got more zones, you can spread them out. But and by the way, more zones means you can run at faster speeds. That's the whole point of producing more zones. Yes, you get a little more control, but it really means you can run a faster conveyor rate and get the same work done because you got more zones to play with. It doesn't matter how long your oven is, you're going to spend about the same 5 to 7 minutes in that oven. So if it's a 20-foot oven, you can run a faster rate than you do at a 15-foot oven, simply because the time in the oven is almost always the same in order to produce a given profile. A leaded recipe, pretty traditional, and then an OLED recipe. This happens to be a ramp 2-spike profile. If you need to soak, then you might want to spend these middle zones that are roughly the same temperature. But this one will actually be solder a lead-free board, or will get you close to and be just a little bit under. It's a great starting place if you have no other guess or no other means of guessing what recipe to start with. Profile, find out if this meets your needs. And again, we're going to be talking more about that. And then we can make adjustments from here. So it's a good starting place. It's a very typical recipe. You walk up to many ovens in the whole world, and they're going to have settings very similar to this, unless they're doing something really exotic. So it's time to profile. And what do you need to do it? I had this slide last. It suddenly dawned on me it's probably the most important thing, but you basically need something to profile. I am surprised by 5 or 6 manufacturers, circuit board manufacturers in our area that we visited, as well as other states, and they quite often tell me, my customer doesn't give me anything to profile. You're going to have a very hard time assuring that solder joints on their product are good without something to profile. So do anything you can. Twist their arm, convince them that they need to provide you something to profile. Just running a blank card through, I mean, you can do that once, get a recipe, and that's fine for that blank card, but it's meaningless. Or it's certainly dangerous to assume that a blank card is going to be the same as the actual product you're getting ready to solder. You're going to need thermocouples. These are your sensors. Thermocouples are extremely robust sensing devices. They come in infinite variety of size, shape, and insulations. We talk more about that on our website in the blog. You're welcome to look there. I'll give you a link to that later. But you're going to need sensors. You're going to need some device to measure temperatures. Of course, I'm going to show you my temperature profiler, my data logger, basically, our M.O.L.E. You're going to need a protective barrier. This is electronics. It's measuring temperature. It's an instrument. It needs to be kept cool. Obviously, you can't solder this thing while you're soldering the board and expect it to function. So all profilers will have some form of protection. The better the protection, the better your results. You might need a carrier if you're not blessed with a conveyor belt, but only the chain where it holds the edge of the circuit board. You're going to need some way to carry it. Otherwise, you can place all of this data logger business on the belt. You're going to need some means to attach the thermocouples to the circuit board and the points you're going to measure. We'll get into that in just a minute. You're going to need some means to solder. The important thing is that it be adjustable. You need to attach thermocouples to solder joints. We recommend solder, and this solder is going to be a higher temperature than the average solder in order to prevent it from coming undone while you solder the board. So you need to be able to adjust that up, but not too high that you end up doing damage. So an adjustable solder iron, you're going to need some solder wick. You've got to get rid of the alloy that's currently there, if there is any, in order to prevent it from contaminating the alloy you're about to use. You'll need some gloves. Hey, this stuff comes out of the oven hot. You'll need a cooling fan to cool the whole works down again should you need to do a second profile. So please keep that in mind. You can cut your cooling time to the next profile by almost 75% if you just actively cool it down a bit. So these are the basic components you need. Many of these come with your profiler. Obviously, I don't think too many come with a fan or a soldering iron, but you'll get most of these with your profiling kit. But these are just some of the extras you'll need to go along with it. Next is determining the points to profile. This is the part that somebody has to do. Somebody has to tell you. December of 2008, IPC introduced a new J standard 075, inspired by our friends at IBM and several other companies, which suggests the components in especially in our high reliability products, stuff that's meant to last 10, 20 years, either right here on Earth or in outer space, or worse yet, inside somebody's heart or wherever. High rel components are at risk to the solder processes, especially as we get into lead-free situations. And it gives a list of these parts as well as a recommended marking system for showing OEMs and contract manufacturers how to detect if parts, by putting a mark on the packaging, whether there's a concern for temperature with these parts. And you can get the standard from the IPC. It's not very expensive. It'll show you the code to look for on the part. So it suggests a marking method to determine that's not on the part but on its packaging material. And it suggests these components that traditionally are at risk. Slowly but surely manufacturers are catching up. However, they remain sensitive, and that includes aluminum electrolytes, some films, and some tantalum caps. Here's a picture of some of the more obvious ones. Crystals and oscillators, resonators and the like, fuses, they are a thermal device. Stressing them with temperature can shorten their life, and they don't all look the same. Most people know what typical fuses look like. Here's an odd one I found, and it could easily be at risk. Inductors and transformers, they're nothing but a coil of wire with an enamel or some form of insulation on it, and that can be at risk at higher temperatures. You short one of those turns on that transformer out, and it isn't an inductor or a transformer anymore. It's certainly not at the value it was intended to be. Non-solid state relays, same coil of wire inside there, at risk at temperatures. LEDs, they have very much a temperature limit, not only a maximum temperature but also a time factor. It's quite common, and that includes the lens as well as the solid state portion of things. Connectors, the plastics relax, loosens up all of the contacts within that connector, and it no longer holds as it should if you get them too hot for too long. And then some switches are very vulnerable. I find it interesting when I keep saying somebody has to do this, and quite often we'll set a board down at a contract manufacturer, and 4 or 5 people will look at it, and quite out of reflex, several people will pick out parts that can't be washed, and they won't charge you for that service. They won't charge you extra saying, well, this part shouldn't be washed because you get water in it, it's no good. And so they'll have no problem recommending that that part be put in after the soldering and washing and cleaning processes. And yet, so far, none of them have said, yeah, I think these parts are at risk thermally. So it's a culture that needs to be developed yet, and hence IBM has produced or helped produce this standard to help get people thinking about the fact that there's more to the potential degradation of these components besides keeping them dry and popcorning and cleanliness, but also the temperature limits that they can withstand before you threaten their life. So what points on a board like this would we want to consider profiling? I'm going to point out a bunch here. When I look at a board, I first check to see which direction it's entering into the oven. So this is the leading edge here. Forgive me for leaving those wave soldered parts on the edge. But this is the leading edge, so this is going into the oven first. You can pretty much assume that any track through the oven is going to experience roughly the same thermal profile, because each portion of this board is going to experience the same track through the oven. So if I put a sensor here and I put one back here, I'm probably going to see roughly or almost exactly the same thermal profile. So I like to look across the width to see if there's any concern, and so to the extent that I can find components over here on the left and components over here on the right and some in the middle, it helps me know that across the width of my oven I'm getting a good profile. There are some components certainly of interest here. This BGA, and you might ask, why do you pick out BGAs? They are unique in that all of the solder joints are hidden, and there's a layer of insulation on the bottom, circuit board itself, and there's a layer of insulation on the top, the component, and it is often on a substrate of circuit board or circuit board-like material. And so heat doesn't go through these things as quickly as they will all the other solder joints on this board, because the solder joints are exposed. They're right out where you can see them. They're right out where the heat can get to them. BGAs, they're all hidden underneath and have insulators on both sides. So you've got to be sure heat is getting under that part. We'll show you how to do that in a bit. So you might want to concern yourself with a couple of points on this BGA. to make sure that the thermal profile or the temperatures across that thing are equal. So we're not getting one side hotter than the other. Of course, there are our aluminum capacitors. We got a crystal sitting here. If that isn't soldered in after the fact, this one was surface mount soldered, so it wasn't. So crystals, we've got a socket here. That socket's designed to have parts go in and out, change on the fly. You don't want to so overheat this socket that it no longer makes good contact because you've relaxed all the plastic. Here's another electrolytic on the other side of the board. Here's a smaller one you may want to check out. Here's an inductor. There's others over here. Here's a standard quad IC with, again, the gull wing type leads all the way around. So it's good to keep an eye on one or two of those. I'm sorry, I got ahead of myself. So this gives you a good, across the width of this board, look at some components that you may want to profile. There are others. Again, you're limited by how many channels your profiler has. The more the better, especially on the initial profile. Once you've got the initial one down, you can back off on how many points you look at. Okay, so how do we attach these? Again, I've already suggested that high temperature solder is the best way. And for some reason, competitors of profiling manufacturers, ourselves and some of our competitors, seem to take odds or put ourselves into different camps on this. And I'm not quite sure why it matters. Our goal is to sell profilers and not sell high temperature solder, or for that matter, tapes. But really, if you're trying to measure the temperature of a solder joint, you should use solder. Nothing else really replaces that, in my opinion and experience. And there's two basic types. There's an SN10. It melts at around 280 degrees. It's perfect for any leaded soldering you're going to be doing. There is an SN5, which is melted around 305. It's perfect for most any leaded solder, lead-free soldering you're going to be doing. People say, well, if I look at the alloys, this is mostly lead, and they're absolutely correct. It is mostly lead, 90% or more. And they say, well, I'm an absolutely lead-free shop. Can't even bring it in the building, and that is a problem. There aren't too many alternatives. You could say, well, this is a profiling board. I'm not going to sell it because I've probably soldered it 2 or 3 times. You're not going to sell that board. At least I wouldn't think you would. So what do? Well, you make sure you take it out of the shop, you mark it as it got lead on it, and put it in a plastic bag and keep it away from your other things. An alternative is to buy this particular alloy, and yes, the AU stands for gold, and it is 80%. Last time I priced it, it was $4,000 a pound. I suspect at today's prices it's much more than that. It's an alternative, but unfortunately, based on the alloys I've looked at, contacting solder manufacturers, it's the only lead-free alloy that melts anywhere near a temperature that you can respectively apply to your circuit boards. Comment, Mark?
Oh, I was going to say, you might mention the fact that the SN5 and SN10 are exempted from RoHS for the express purpose of making high temperature solder joints.
Yeah, that is true, and that's and with that exemption, that allows you to sell product with lead in it for that purpose. If, however, you're a shop that just doesn't allow lead in the door, that's obviously a concern, and I understand. This isn't the best alternative, but it is an alternative. There are other ways to make solder, I should say, make connections which are not as effective, but we'll go into those. I wanted to show you how one does attach a thermocouple using solder. Real quick, I'll just walk through these slides. There's 5 or 6 basic steps. First, let's look at the scale here. We're talking 20 thousandths of an inch. This is a 5 thousandths inch or 36 gauge thermocouple. I started by wicking away the old solder. and then I added just a touch to the TC of SN5 and down here on the IC leg. I then taped the thermocouple down so it was held in place. I then just touched it with a soldering iron to melt that solder, added ever so small of amount more, and then looking up close, I had myself a a solder joint that's thermally well attached to this IC leg, and again my scale is about 20,000ths of an inch here. Let's take a look back here, a little more perspective. Here's my tape that held it down. Here's my IC. So perfectly good solder joint, perfectly good attachment. It's going to behave thermally just like a real solder joint. And even though it's slightly larger than all the others, it's no match for 10,000 watts worth of heat being poured at it from your solder machine. Some questions came out that I wanted to illustrate real quickly here. Where is the solder joint when you attach using solder? I should say, where is the thermocouple when you attach using solder? Some people would say, well, the thermocouple's got to be right down on what you're trying to measure the temperature of, because if it's floating up in here, it's going to be a different temperature. Well, so is the thermocouple actually at this black dot? The answer is no. It actually is right here where these two wires, the two thermocouple wires, leave that conductive solder. You might say, well, that's a problem. I'm trying to measure the temperature down here, and yet the thermocouple is actually up here. And the quick answer is, remember your scale. This thing is 20,000ths of an inch or less. It might be a little bigger, it might be a little smaller, but it's around 20,000ths of an inch. And the only way that this thermocouple is going to measure any different temperature than what the entire temperature of this tiny little drop of solder is if there was a temperature difference from one side or one end to the other. And because it is so small, there's no practical way a temperature difference can occur. So you're going to get a perfectly good thermocouple measurement of this blob of solder in the pad, no matter where that thermocouple ends up within it. So you're okay to have that thermocouple slightly elevated or not exactly down on the pad you're trying to measure the temperature of. Perfectly okay, considering the scale that we're talking here. Where you're not okay is if this happens. If your bare wires, before they enter in the insulation, connect together, then you've created a thermocouple that's significantly in a different location than this tiny little solder joint. And there's a good chance there's a temperature difference from here to here. You're going to get false readings, no question. So that's one thing to avoid when soldering or attaching your TCs down. Make sure you don't have shorted wires. Make sure it is somewhere inside that solder blob and that it isn't 3 feet in diameter. There are other methods. This is that link I was telling you about. You'll get this in the PowerPoint when we send it to you. There are other methods. There's tapes and glues. There's aluminum tape. There's various varieties of aluminum tape. They have double-sided. I don't know why, and some people like to use the double-sided. I've yet to understand why double-sided sticky tape makes a difference. You're only sticking it to one side. However, aluminum tapes, it's important you have a silicone adhesive. Most aluminum tapes, especially if you go to Home Depot to buy it, it's got an acrylic adhesive. It won't do you any good at all. It'll melt and fall off first time through. Silicone adhesives are the only ones to use. 3M433 is a silicone adhesive aluminum tape. Some pros, well, it conforms well and it holds its shape. Once you press your fingernail down in there and press it all down, it holds its shape. Unfortunately, you can't see through it. You can't be dead sure exactly where it's located, even though you can see the thermocouple impressed through it. You can't be sure where it is attached. There's Kapton tape, again, silicone adhesive. You can see right through it, so you know that your thermocouple is on the solder joint of interest. or excuse me, I kicked my bucket here. Your solder joint or component of interest. The con is it doesn't hold its shape well. As soon as the silicone adhesive softens under temperature, this tape wants to flatten back out again, and so it will peel itself up pretty easily. There's also high temperature epoxies. I'm not going to attempt to recommend one. There are many. Type in high temperature epoxy in Google and you'll find lots of them that go well above 300 degrees C, and they do hold well. However, some of the cons, it does add an insulation. Even the best thermally conductive epoxies aren't anywhere near as good as solder as far as their thermal conductivity. There are some that are higher than others, but even the best aren't as good. So there's some insulation that's going to average out or suppress your temperature readings slightly, so you won't see the same peaks that a solder joint would see. And it requires some type of curing, either some type of expensive light source or just time, in some cases time and temperature. And that could be anywhere from several hours to overnight. And most people, when they set down the profile, they want to get it done right away. There is our attach ease, which conforms to the TC very well. It's a nice, soft, flexible tape. It is reusable, which is kind of a cool thing. It's semi-transparent, so once again, you can't be absolutely assured where it's connecting. Glues and tapes are excellent for attaching thermocouples to flat surfaces, to components, tops or sides. They are not very good at attaching to a rough textured component or something where it isn't completely flat, such as a leg on an IC or something like that. So keep those two things in mind when you choose an attachment method. Flat surfaces, tapes will do pretty good 1 or 2 times. Epoxies, again, will hold for a long time, but they add resistance. Soldering for solder joints is really the best way to go. I mentioned BGAs. There's no magic bullet here. There's 3 basic ways to make a thermocouple connection. It's most important to get the thermocouple directly underneath the BGA component. Knowing what's going on the bottom and knowing what's going on top of the BGA simply does not tell you what's going on in between. You got to drill a hole. If you can do it before the BGA is placed, all the better. Drill a hole and take away a pad. Get a thermocouple at the height of the pad. You can backfill it with epoxy. Epoxy is the basic same thermal material as the circuit board from a thermal conductivity point of view, so it's excellent for backfilling. Simply piece a piece of tape over there and fill her up, cure it up. Put your component down, and you've got a perfectly good thermocouple for knowing the temperature of the soldering that's going on underneath the BGA. If you were given a board with the BGA already soldered, you can post-drill. The only difficult part of that is it's tough to run a drill bit through here with a part there without completely destroying what's on the back side. And if you're very careful, you can do it. Put the thermocouple in, backfill it. Or you can use an existing via if there's a hole going all the way through the board. Most pads on BGAs have vias either to inner layers or, if you're lucky, all the way through in order to get all those traces out. And an existing via can work. You probably are going to have to use a smaller, more like 40 gauge thermocouple to get it through that hole. But it is a way to get a thermocouple in between the layers. There are other ways of slipping thermocouples in from the side. There's a varying amount of success there. The super delicate thermocouples tend to be damaged easily by trying to shove them underneath there. You're better off putting them through a hole and gluing them or epoxying them into place so they're not so easily damaged. These are the best ways. Pre-drilling being the ultimate way to do it if you haven't a chance to do it, or post-drilling again where you end up with a thermocouple in contact with a ball. It's time to solder. This is my machine. Took these pictures just a couple of weeks ago. Thermocouples attached to the board. The board goes in first. We recognize that the profiler and its thermal protection can influence the zone temperature, so it's good to have at least 12 to 18 inches, or roughly one zone length, between your board and your profiler, lest this influence the oven and thus alter what your board would really see. So board goes in first, profiler on a carrier second. And as you see, I don't have a mesh belt to let this ride on, so I'm forced to put it on a carrier and slide it through. Don your gloves because it does come out hot. Board out first, carrier out second. I used to have a box fan I had underneath this rack until after 10 years of use, its bearing seized up. So I'm waiting for summertime to buy a new one. I just bolt it underneath here and it blows straight up. It does an excellent job of cooling it off. However, get it on a fan. Any fan or convection of room air will cool this whole affair off, probably in 15 minutes rather than an hour, just letting it sit. It'll be ready for the next run just that much faster. Don't shortcut this. If you leave heat inside these barriers or heat inside the MO.L.E or your profiler, or even worse yet, heat on your circuit board, you're not going to get the same profile. You're risking damaging your profiler because you get it too hot. So get it down to temperature, room temperature, before you run the whole works through again, should you need to do a second profile. The profiler, the profile needs to be downloaded, and you take the profiler to usually a PC. Download it and you check out the results. This is an actual profile of an actual circuit board through the oven you just saw there. I'm only showing 3 of the 6 thermocouples that were run through this, but now it's time to determine whether you met the needs. All good software will give you these values either in a table or some sort of readout in value for each channel. However, you're going to want to look at the ramp, make sure it isn't too much, make sure it isn't too little. You'll want to check out your soak to make sure that you spent the amount of time that you intended in the soak zone. Of course, the spike, again, another ramping. You want to make sure that you're not increasing the temperature too quickly. Check your time above liquidus. Make sure you didn't exceed the peak on your component. And by the way, usually most components have a peak limit, but they also have a peak temperature for a certain amount of time. You might say, well, I exposed it to 240 degrees for 4 minutes. Well, it maybe only take 240 degrees for 10 seconds. So that's a parameter you want to make sure you haven't cooked your components. And then finally, your cooling rate. Again, good software will show you all these values underneath here and will show you whether you've met your limits or exceeded your limits or not. But these are the typical values you'll extract from a profile to make sure that it met the requirements for both solder paste and limits on your components. And then again, software will let you do a prediction if necessary. If you didn't meet the requirements, what do you do to your recipe in order to allow it to meet the requirements? They will have anywhere from some kind of automated recipe generator to just you play with it, sort of a manual prediction method. Either way, by the way, we cover this in MAP 101 and Profiling 201, but either way, you now have an opportunity to adjust your oven and make your profile better. And it's usually using some form of predictive type of software. The beauty of it is now that you have a real profile, you can make real adjustments against the actual profile of your oven to make sure you generate a recipe, or I should say adjust the recipe to better meet the needs of your solder paste and your component limits. Because you're using the actual profile of your actual circuit board in the actual oven, you get the current recipe and its performance. not a guess, not a calculation, not a virtual, but the actual machine performance. You get to compare the actual profile of the actual components and the actual solder joints of your assembly. And it lets you adjust that profile to the desired specifications. And you can do it live on an actual real live profile on how it performed in your oven. So when you make changes to the recipe using predictive tools, you can be assured that, hey, if I change the recipe of my oven according to what the prediction shows, I will get an accurate reproduced profile as a result of those recipe changes. So a real profile assures you that if I make changes using the software, I'm going to expect and count on those changes actually happening when I change my recipe. And the profile will now look like what I prefer or what my components and my solder paste needs. We went over a lot really fast. We have to squeeze this amount into an hour. There's about 5 minutes left here, and I want to give you a chance to ask any questions. Go ahead and text them in if you have any. But what we've done here is we've looked at ThQM very quickly just to pull out what we need from a profile. We looked at paste requirements, how we generate an oven recipe. We looked at what we need in order to get profiling done. We looked at points on a relatively complex assembly to decide which ones we are going to profile and why. We showed you how we can get some TCs attached, which attachment methods work for what application, and then finally we actually ran a profile and we took a look at it. And that is profiling a